All right, so this week you're going to do everybody's favorite lab. We're going to explore the nature of the connection between the electric potential and the electric field. Now, if you recall, we learned back in chapter 19 that the electric field, oops, I clicked right past it. The electric field was related to the electric potential because the electric field for a uniform field anyway obeyed this relationship, right? Where if you looked at how much the potential changed divided by how far you had to move for that change to happen, you'd find the electric field. Now, the minus sign just tells you that the electric field points in whatever direction the electric potential gets smaller. And things work pretty well from there. So, for instance, if I were to go over here and measure the electric field or the electric potential at this location, and I find that it is 10 volts, and I move over here and I find that it is only 8 volts, and I've traveled a distance of, let's say, 1 centimeter, then what that tells me is that in this region, the electric field is going to be given by this. So the change in potential is going to go from 10 down to 8. So it's a change of -2. The distance that I've traveled is 1 centimeter or 0.01 meters. So -2 divided by 0.01 is -200. So that tells me that in this region, the electric field is 200 volts per meter, and it points in the negative direction, which is to the left. That's the idea. And this works great provided that your electric field is uniform. In other words, this is assuming that the electric field is the same everywhere in that region. What it shouldn't work for is if the electric field is varying with position. And what we're going to end up doing is we're going to put that caveat to the test today. Because what we're going to do is we're going to calculate the electric field for a single positive point charge. And we know what that looks like, right? We know that it extends radially outward. And we also know that the intensity of that electric field varies with position. The further away from the charge you are, the further apart the lines are, the weaker the electric field. We know how to calculate it directly. The electric field is given by KQ over R squared. So as R becomes larger, we're dividing by more, E is getting smaller. Now, in principle, this should not work for an electric field that looks like this. It shouldn't. It should only work for electric fields where the field is uniform, meaning that it always points the same direction and it's always got the same intensity. This isn't that, but we're going to try it anyway. And the reason we're going to try it is because technically, and this is where we have to run into the issue of this isn't a calculus-based class, so we're trying to avoid doing any calculus. But technically what happens is if I shrink this distance that I move down super tiny, then if that distance is infinitely small, the electric field can't change for very much. So even a non-uniform field over short enough distances seems basically pretty uniform. And what would happen is this expression would turn into a derivative, which if you've taken calculus, you know what that means. If you haven't, don't worry about it. But that's the idea. In actuality, if you turn this into a derivative, it works exactly. It works perfectly. And we want to test how small does that distance have to be in order for that relationship to work, even for a non-uniform field. So that's our goal today. We're going to test that assumption. Now, how the heck are we going to do that? Well, we're going to take a simple system, the simplest system that we can imagine, and we're going to calculate the electric field, and we're going to calculate the electric potential. Those are easy enough to do. We have formulas for both. The electric field is given by this. The electric potential of, say, a point charge is given by that. So we have the capacity to calculate both of those things. So we're going to do that over some broad area. Then what we're going to do is we're going to zoom in and pay attention to the electric potential of that effect. And we're going to look to see how the potential changes from point to point and utilize this expression. And from the electric potential, we're going to get an expression for the electric field. Now, if this formula really works, what we get from doing the electric field this way ought to match what we get from doing it the real way. And that's what we're going to compare. When I use the potential and calculate the electric field from that, do I get the same answer as when I just calculate the electric field directly? That's our goal. That is the thing that you're trying to accomplish today. So to pull this off, what we're going to do is first, I need to genericize each of these in a way where I can build a simulation that calculates the electric field at different locations. So what's going to happen is, this is great if you know what R is, but what we're going to do is, imagine I've got a point charge, right? And here's my x-axis, here's my y-axis. And what we're going to do is we're going to have this point charge be pretty much at the origin. I say pretty much, and we'll see why in a minute, because we're going to move it a little bit off center just for calculational purposes. But basically, we're going to put that at 0, 0. And what I would like to be able to do is to specify a location. So maybe I want to look over here at this location, which is going to be, maybe it's x equals 5, y equals 2, or some x and y. Well, we can pick the x and y arbitrarily. So some number x, some number y. All right. I want to look right here, and I want to calculate what the electric field is due to that point, or due to a charge sitting at that point. Well, even though we have a formula, it's not immediately obvious what the heck I should use for R. Conceptually, R would be that distance right there. But how would I know what R is? Well, if I know the x coordinate, that means I know this distance. If I know the y coordinate, it means I know this distance. And so in order to find R, I'd be looking for the hypotenuse of this little triangle. And, oh, that's easy. R would equal the square root of x squared plus y squared. So if I wanted to genericize this formula for any location I choose to look, all I'd have to do is write the E would equal K times Q divided by the square root of whatever point I pick for x squared plus whatever point I pick for y squared. There we go. That was super easy. Now, I do have one problem, and that's if I could pick any value for x and y, this works. But what would happen if I chose to measure the electric field at x equals 0, y equals 0? Well, that would be like me putting it directly on top of my point charge. And if that happens, I'd be dividing by 0. It would blow up and give me infinity. And so what's going to happen is, in our lab today, I want to be able to calculate the electric field at 0, 0 without it blowing up and getting infinity. I don't want to break my formula at any point, because that'll introduce a little computer bug that I'm trying to avoid. And what we're going to do to make this better is we're going to move the point charge and have it not be exactly at 0, 0. We're going to have it be a little bit off center. And what that means is when we go evaluate at 0, 0, we'll be really close to the point charge, but not exactly on it. It won't be dividing by 0. It'll be dividing by really, really tiny, but not quite 0. So here's what we'll do. Rather than have the point charge exist at 0, 0, maybe I'm going to have it be at x equals 0 and y equals some super, super tiny amount, like 0.00001 or something. Now, as long as I don't measure at specifically this location, I'm not going to run into any divide by 0 errors. But it's not going to change my answer very much from what I would have got if I had put it at 0, 0. So most of the points are going to be so minimally affected, I'm not even going to notice. But at that one spot, it's going to look primo. Now, if I do this, my expression for R is going to be a little bit different. Because what's going to happen is now my triangle is the same distance x as it used to be, but the y distance is a tiny bit smaller. Easy to do. I'll just replace y in this with y minus whatever that is. So if I call this distance d, then I can say that E would equal K times Q divided by, oh, I made a mistake. I'll show it to you in a minute. So, have you spotted my error yet? So R is equal to this, right? Except the formula is not KQ over R, it's KQ over R squared, which means I got to square all that. Oops. So, now we're good. When I square a square root, the square root cancels. And so this is going to calculate the electric field exactly at any point x and y of my choosing. So, super easy. Now, I could find the electric potential the exact same way. The electric potential is KQ over R. So it really is going to be that stupid formula that I wrote by mistake a minute ago, where the square root hasn't canceled. It'll be x squared plus y minus d squared. And so you'll notice I'm putting my thing off center. If you've taken this class before and you did it before, last time we did it, I moved it in a different direction. So I'm doing this so that those of you who have taken this class before can't just turn in the old lab. You have to do it again. I'm making you do it a little differently so that you have to redo it. I'm a jerk. But that's how this is going to work. So how do I calculate what this is at all these different points? We're gonna build a simulation that's going to calculate all this garbage for us. So to do that, let me switch my mobile screen share. And let's open up an Excel window. Now for this, you're going to have to be using probably the full version of Excel. You also have to be using the non online version of Excel because we're going to be using a feature that doesn't have. You'll have to download the full version of Excel. Now, I often have students tell me, "Oh, I can't do that. I don't own a copy of Microsoft Office." Yes, you do. Yes, you do. The school gives you an Office 365 account. You can install 5 versions of Microsoft Office on 5 different computers. If you don't know how to make that happen, I can show you. Come see me offline. We'll make it work. I don't want to spend time on this video doing it because I'd have to figure out where it is myself. But I don't own a copy of Microsoft Office. I have this because the school bought it for me. It bought it for you too. Get your money's worth. You're paying too much intuition to not have access to the stuff that they got you. All right, so here's what we're going to do. I want to build a little sheet where it's going to calculate the electric field for some point charge in different locations. So first, I'm going to pick a value for Q. I want Q to be some number, and it doesn't matter what it is. So I'm going to put a cell in here for Q, and I'm going to have Q be 5 microcoulombs for the time being. But honestly, it doesn't matter. And in fact, we'll probably end up changing that as we wish. I'm going to pick a value for that value D. I said that D had to be a tiny little number. All that really matters is that when we move our charge off center a little bit, I want to move it off center by less than a centimeter, right? If I move it by a centimeter, all I'll be doing is creating the same problem at y equals 0.01 as I did at 0.00. I want to make sure it's a smaller number than that because I'm not going to measure in increments that are that tiny. So let's make that be 0.00001. That's probably good. And of course, that's in meters. I'm making sure to label my units because if you don't label your units, I will give you a bad grade. So now I need to generate a region over which to measure the electric field. And I want to put the point charge at 0, 0. So I need to have a region that's centered at 0, 0. So I'm going to go from x equals, let's say, -2 to +2. So here's my x-axis. So there's x equals -2. And I want to measure in tiny little increments. So let's go in increments of, let's say, 1 centimeter. Now that means that if x equals -2 is my first point, when I move 1 centimeter to the right, that's going to be x equals -1.99, right? And I want to keep doing that all the way out until I get to +2. I don't want to have to type that a million zillion times. So what I'll do is I'll highlight both cells. I'll put my cursor over the little box in the bottom right corner until it changes to a little black plus. I'll click and hold. I said I'll click and hold and drag, and you can see that it's counting up as I go. And I'm just going to scroll this all the way off screen. Until I get to my desired location, which is x equals 2. So you can see that what I have here is a big swath of stuff. I'll go over here and do the y-axis starting at +2 and dropping down to -2. So here's x or y equals 2. Here's y equals 1.99. And again, I'll do the same trick where I click and drag. Oh, too much. Whoa, way too much. So now I've gone down to -2. And so what I have now is a little grid on which I can do my calculations. And so the idea is if I want to know what the electric field is at x equals -2 and y equals +2, I'll look in this cell and hopefully I'll have a formula that in that cell will use the formula we were just talking about, calculate the electric field and put the number there. However, if I look in one cell over, I want it to do that exact same formula, but I want it to calculate the electric field at x equals -1.99 and y equals 2. So by looking in a different box, what I'll be effectively doing is choosing a different value for x and a different value for y. All I've got to do is put in that formula that we were talking about previously into that sheet. So the formula that I want to put in there, if I want to calculate the electric field, is this. Now, you might say, well, gosh, Tom, how am I going to pull that off? How am I going to make this thing work? Well, the way that we're going to do it is we're going to genericize this, and we're going to put that formula into Excel. And we're going to have to use a thing called an array formula. And an array formula is a particular way of calculating stuff in Excel that's probably a bit advanced. And I'm going to walk you through the first little bit, but I'm going to leave some things intentionally vague so you have to figure some of this stuff out yourself. Oops, stop. There we go, better. So, what's going to happen is I'm trying to put into this formula, and I'm going to write it on the screen here just so that I don't have to flip back and forth between cameras. All right. So the formula that we're trying to put on here is E equals KQ over X squared plus Y minus D quantity squared. All right, that's the formula. I hope you can read that over the toolbar that I'm trying to put in here. Actually, stupid, why didn't you just... I don't know why I didn't think of this before. Let's write it down here where there's not a lot of garbage that makes it hard to read. All right, so I'm trying to put this formula in all of that space. So in order for me to pull this off, what I'm going to have to do is first, I'm going to have to select every single cell that is going to have that formula in it. And there's going to be a lot of them, right? I went 200 boxes on or to the right and 200 boxes down. So there's going to be 1,600 boxes or 400 or 4,000 boxes. I can math in total. So I'm going to click right here. And one thing I like to do that I highly suggest that you do, otherwise it'll probably drive you crazy, is we're going to freeze the panes. I go over here to view, go to freeze panes, boom. And now you can see that when I scroll to the right, it always keeps these numbers right over here in view. So I can always see where I am, even when I'm off center, because this whole thing won't fit all at the screen at one time. So in any case, I'm looking over here, I'm verifying that this is -2, 2. I'm going to click right there. And then I could, if I wanted to, I could click and drag and select stuff, but that takes a while. I'm lazy. I'm going to click here. So click. Now I'm not touching the mouse. I'm using the scroll bars with that cell up there in the upper left-hand corner selected. I'm going to drag all the way down, drag all the way over, and then I'm going to hold down Shift and click in the lower right-hand corner. And you can see that what it has done is it's selected every other cell in between the two cells that I clicked on. So now I'm going to use the scroll bars to scroll back up, just because I like to be over there. But I have the entire field selected. And then I'm going to not click in a cell. Don't click in the cells. Click instead in the formula bar. Right? And in that formula bar, I'm going to have to put my equation. Now, the problem is the equation I want to put is this big red thing that I have circled. But unfortunately for me, I need to know how to translate that into something I can write. And what I'm going to do is, like, the letter Q appears in that formula, but Q is a variable. I picked it up here. So every time I see Q in my formula, I'm not going to type Q. I'm going to type the cell that has Q in it, which in my case, the way I've set it up, is going to be cell A2. So A2 is Q. Uh, everywhere I see x, well, x is going to be whatever value is appropriate from this top bar of stuff that I can't apparently draw a circle around. However, when I'm looking at, let's say, cell G6, I want x to be negative 1.95. But when I'm looking at cell J6, I want it to be negative 1.92. So when I see x in my formula, I'm not going to type x. I have to type what x should be. So I'm going to take x, and everywhere I see an x, I'm going to replace it with the first cell that has one of my x's in it, which is up here in B5, colon, the very last cell that has one of my x's in it. Well, if I scroll all the way over, I can't do that with the annotations on. Aha, here's the last cell that has one of my x's in it. That's cell OL6, or sorry, OL5. So when I write, everywhere I see x, I'll replace it with B5 colon OL5. And that way it'll pick the appropriate number out of that top column. Now, by the same reasoning, everywhere I see a y, I'll have to make a clever replacement for that as well. So everywhere I see a y, I look over here. Here's my first y. That's in cell A6. And if I scroll all the way down and look at the bottom one, you can see that my very last one is an A406. So everywhere that I see in my formula the letter Y, I'm not going to type Y. I'm instead going to type A6 colon A406. What about D? Well, everywhere I see a D, well, for me, you can see that I have a D set up right there. And so everywhere I see a D, well, for me, that's in cell C2. Yours might be in a different place, so do it however you're going to do it. I have before seen people who, they'll make a cell and put K in it. That's perfectly reasonable. I'm going to not do that. I'm just going to type the number for K. But either way, it may make your life simpler to put a cell with K in it. So now that I've done that, I've got all my cells highlighted. I know what my substitutions are going to be. Now I have to type that cell or that formula into the formula bar. So I go equals 8.99 times 10 to the 9th. Notice I'm using exponential notation because I can. Times Q, which, what did I say Q was? Q was A2, divided by, now here's where I run into a problem. I've got complicated stuff in the denominator of a fraction. And if I just do x squared plus, Excel is going to see that plus and use order of operations, and it's going to do that last. So it would take KQ, it would divide it by x squared, get a number, and then it would add y plus d squared to my answer, which is not what I want. I need it to do the entire denominator before it does the division. So that means I need to put a set of implied parentheses around the denominator. So anytime you have anything complicated in the denominator of a fraction, you have to do that. I can get away with not doing it in the numerator because order of operations takes care of me just fine up there. So going back to my problem, I'm putting an implied set of parentheses. Now I need x squared. Well, x was B5 colon OL5. Notice when I did that, see how the letters are red and it takes all of those x's that I want and it puts them in a red box? That's how you can tell you're doing what you think you're doing. Notice the A2 is blue and it put a blue circle around the Q. So you can tell what that is. Now I got to square that. So squared plus, well, now there's parentheses in the formula. Now I need y, A6 colon A406 minus d, which I had in C2. I'm closing the parentheses. I'm squaring that whole job. Then I'm closing the outside parentheses. And so there's the formula that I have translated into the appropriate setting. And before I hit enter, I am instead going to hit Control Shift Enter. If you're on a Mac, I believe it's Command Shift Enter, but try them both. I don't remember. I don't use Macs, but I know that they're oftentimes the Control key is swapped out with the Command key, but it's one of those two. Try them both, see what happens. Control Shift Enter, boom. And what it has done is it's put that formula in every one of those highlighted cells. But in each cell, it is utilizing the appropriate value of x. So when I look right here, it's using -2 for x and +2 for y. When I look right here, it's using -1.87 for x and 1.95 for y, right? That's what's happening. That's how that's going to work. So I have a calculation of the electric field everywhere over my entire region. And this is the real electric field, right? This is the thing that we're going to compare our answer to in this lab. This is our theoretical value for E. This is what we expect to get when we do it this other way. So what's going to happen is we've got a sheet. We've calculated the electric field everywhere. Now I need to do the same sort of thing, but this time I want to find the electric potential everywhere. Same difference. So what's going to happen is I've got that sheet that I've labeled the electric field. And real quick, and I'm not doing this one on a screen share because I want you to do it yourself. And if I do it on the screen, you guys are just going to copy and paste or copy exactly what I do. And I don't want you to do that. I want you to figure it out. So I'm intentionally leaving a little bit to the reader. So what's going to happen is I have gone ahead and I've basically just remade the same sort of deal that we did last time, right? And I've cleared out everything, so I'm going to start from scratch, and I'll do the same thing that we did before, where I highlight the entire shebang. And then what's going to happen is I'm going to do the same thing, except now, rather than put in the formula for the electric field, I'm going to do that formula instead, right? Same deal, but I'm going to set that formula in each of those places. And so when I stop sharing, because I want you to do it yourself, so on the bottom, you're going to have a square root function. I'll point out the square root function is sqrt, and then whatever you put in parentheses is the thing that you are going to be square rooting. And lo and behold, so going back to the screen share, let's just do the full screen. So what you can see is that here I've just done the different formula and used the electric potential and made a similar sheet with the electric potential everywhere. Now what's going to have to happen is I need to use this electric potential to calculate the electric field using that change in V over D formula. That's my goal. But the problem is electric fields are vectors and electric potentials are not. So here's what's going to happen. Right? I know that the thing we're trying to prove is that I can get away with using that, and it should give me the same answer as the electric field we got a minute ago when we did that full sheet. So what that means is that if, let's say I look right here, and I want to know the electric field at x equals -2, +2. I want to calculate the electric field right there. Well, that says that if I look at how the potential changes going from one place to another, and I'm pretty sure I have a typo in my formula because this doesn't have the right behavior, but whatever, we'll make it work. What I would be able to do is say, aha, if I move 1 centimeter, that's 1 box to the right, delta V is going to be the final, so this number minus the place I started, this number. So I can calculate delta V from that. Meanwhile, D is going to be this number minus this number. But of course, since all these are 1 centimeter apart, D is going to end up being 0.01 every single time. So what I want to do is I want to be able to calculate the electric field by moving from one box to the next, finding delta V, dividing by D, and that'll be E in that spot. In the next spot over, I want to go take this number minus this number. Or later on, maybe this number minus this number. I'm always moving one box to the right, seeing how much V changed by. You can see here it went down from 22,000 to 15,000 and something. Here it went up from 15,000 to from 15.8 to 15.9. Again, I think this is probably a typo because that's not how that should behave, but it doesn't matter for our purposes right now. That's what I need you to do. So let's stop annotating. Again, I'm going to write down that this is my, I'm renaming my sheet so I know which ones are which. This is the electric potential. This is V. And I'm going to use V to figure out the electric field. So maybe I'm going to make another sheet. I'm going to copy all this. Oops. Let's try that again. I'm literally copying the whole sheet, going back to a blank sheet and pasting it. That didn't work. That's the wrong sheet. Doesn't matter. I'm going to clear out all the content so that this is all empty. So now I have a nice, happy blank sheet. And what I'll be doing in this one is in this cell here, see, I've clicked on that cell. I want that to be equal this formula that I have written on the screen, the negative delta V over D. So negative, I need delta V, so I'm going to put parentheses. And of course, the V's that I'm subtracting are on the other sheet, the electric potential sheet. So I'm going to click over on the electric potential sheet. And you can see what it has done is up here, it's gotten my formula bar. It has the name of the sheet and an exclamation point. And now I'm going to click on my cell. So I'm going to go from B6 to C6. So I'm going to do the final, that's the C6, minus the initial. So I'm subtracting these two numbers right here. Then I'm going to divide it by 0.01. Why? Because that's the D, or the distance I'm traveling. And so according to my calculations, at that location, the electric field is 2,816, but it points to the left. The negative sign means to the left. Problem, this only gives me the X component of the electric field. That's only part of my answer. Now, the good news is I can do that same formula everywhere, and I don't have to type it a million zillion times. I can have Excel do all the math for me. I'm not going to need another array formula. All I have to do now is that if I have the answer at this one point, if I drag all the way down, it'll fill in the blanks everywhere. And if I take that whole column while it's highlighted and drag it sideways, well, there, it'll fill that same formula in everywhere. So what I'm going to have is the electric field calculated in the X direction everywhere. It's only the X component of the electric field. So I'm maybe going to label this as the X component only. Right? That's pretty cool. Now I could do the exact same thing and get the Y component. So again, I'm going to go back to my original sheet. I'm going to Control C, Control V. I'm going to freeze the panes. I'm going to clear all that out. That just gets me the same sort of structure to play with. And again, over here, what's going to happen is I want to do the same deal, except now what I want to be doing is I don't want to be subtracting this guy. Hello. I don't want to be subtracting this guy versus this guy anymore, because that's going to give me the X component. Instead, I want to be going up. I want to be going in the positive Y direction. So I want to subtract this guy and this guy, because that's going to give me the Y component of E. However, since I'm going up, I'm going to start at the bottom, not at the top. So I'm going to go back to my electric field in the sheet 4, which is going to be my Y component. I don't want to start up here. I'm going to drag all the way down to the bottom. And in this cell here, I'm going to have equals, and it's still going to be negative delta V over D. But for delta V, I'm going to go back to the electric potential, and I'm going to scroll down to those same two boxes. So I'm starting at -2, -2, and I'm going to go up to -2, -1.99. So there's my final here. I'm clicking the top box first, minus the initial. And again, I'm dividing by the 1 centimeter distance between those two boxes. And that gives me the electric field in that location. But that's the Y component. Now I can take that box, drag it up, and fill in a bunch of blanks. And I can take this and drag it sideways. And so what I've got is the Y component of the electric field everywhere. And again, we're using that delta V over D formula that we don't think should work. Now, if I have the X component and the Y component of a vector, how do I find the total vector? We've done that before, a million zillion times. If you know the components of a vector, how do you find the magnitude of that vector? We don't know. We've stopped paying attention 20 minutes ago. Sometimes you guys frustrate me. So if I'm doing that, then what's going to happen is I've got a vector, and I know the X component. I know the Y component. The magnitude of that vector is whatever the diagonal is here. Well, the X component is that sheet. The Y component is that sheet. So if I want to know the electric field at any location, all I've got to do is take the X component part squared plus the Y component part squared, and that's going to give me the total. So once again, we're going to start with your basic setup. And again, I'm going to clear out all the stuff that I don't need and replace it with what I do want. I'm going to freeze these panes again. So here what's going to happen is in cell -2, +2, I want to be looking in the X component sheet and the Y component sheet and using the Pythagorean theorem to combine them. So equals square root, parentheses. Now, I got to go over to the X component sheet. I'm going to pick that exact same cell, so -2, +2, boom. Square that bad boy, plus I'm going to click over to the Y component sheet, boom, squared, close that up, hit enter, and there's the electric field in that location there. Then I'm going to drag it all the way down. Drag it all the way over. And at that point, I'm going to have the electric field calculated using this delta V over D formula. So in principle, what should happen is, in principle, the electric field that I get this direction ought to be the same as the real electric fields. In other words, this electric field that we got using this formula that shouldn't work ought to, in principle, match what we got when we did it to begin with. So our goal in this lab is not to do all this. This is just to set it up. Our goal is to analyze how different we got the answer we got from this is to the real answer that we got in the beginning. That's the thing that you're going to try to analyze. So hopefully that gets you a sense of how to make that work. The idea is to play around with this, and so if you're here live with me, so you can get those things set up. I'm gonna pause the recording for a second. There's a bug in that sheet, and before I show you anything else, I want to fix that bug. But again, I'm going out of my way to make you do the electric potential formula on your own. So I don't want to show you any formulas for that one. You got to do that on your own. So give me a second. Let me pause that before I. Okay. So I went back through and I fixed the typo in my electric potential formula. So it's actually calculating correctly. So now let's go back and take a look at our results and see if we can't make sense of things. So this is the electric field that we got by doing this approximation. Now, the electric field that we're calculating on this sheet, we don't expect to necessarily match the real answer because we're using this delta V over D formula that only should work so for this field here, we use this formula, and we only expect that to work if the electric field is uniform. And for a point charge, the field is definitely not uniform. Now, let's compare what we see on this approximation sheet to what we saw when we did it the real way for the first sheet. Now, here in -2, +2, I get some crazy huge number. And if I look over here on my original electric field, oops. I did some color coding to help me debug. That's what this is all about. Let's turn that color code off for the moment. There we go. That color code is making it hard to read. So you'll see here in cell x equals -2, +2, I'm getting 5,618 when I do it the real way. But when I do it the approximate way, it is not even remotely close. Now, what is up with that? That's crazy terrible. Well, it has to do with the fact that we're on the edges of the screen. Because if you remember, what we were doing is we were doing the cell we were in minus the cell above, right? To get the y component of the electric field when we did it over here. But what's going to happen is when you're in the very, very top part, you're taking the cell you're in minus, well, the cell above you doesn't have anything in it. And so we know that everywhere on this top row, it's going to be bogus just because of the way we're calculating it. That's an edge effect. That's not super important. There's no physics there. By the same reasoning, the x component where we were subtracting the one you're in minus the one to the right tells me that if I go and I look at the far right side, I'm going to have the same problem. This far right side shouldn't match either. So I'm going to ignore the top row. I'm going to ignore the far right row. But what about everywhere else? Well, if I look here where I'm not on the top row, so at x equals -2, y equals positive 1.99. Here I get 5,647 when I do it the approximate way. When I go back and look at the electric field the real way, oh, 5,646. The other one is 5,647. That's really close. So even though this formula that we're using, this delta V over D, isn't supposed to work for a non-uniform field, here we're making the delta, the difference in distance, the D on the bottom there, we're making it 1 centimeter, which is about yay big. Here, only a 1 centimeter increment, we got pretty good agreement when we were like, 2 by 2 meters away. Now, we won't always get that same level of agreement. What if I instead try looking at somewhere near the origin? So I'm going to scroll down. Oops, too much. So here is y equals 0. So the y-axis is this entire row here. And I'm going to scroll that over until I get somewhere close to the middle. So right here is 0, 0. That's basically the point charge is just barely to the side of that. Remember, we moved it by 0.0001 up above. So basically the point charge is between this box and this box. If I look at the approximate electric field in that same location, I passed it. There we go. So there's the x-axis. Here's 0, 0. Yeah, that's 6.35 times 10 to the 11th. But when we did it the real way, it was 4.5 times 10 to the 14th. Well, 10 to the 14th is like 1,000 times larger than 10 to the 11th. It's not even remotely close. It's like saying, hey, I'll pay you, $5 for something, but in actuality, the thing costs not $5, but $5,000, right? That's a huge difference. You would notice that difference. So the formula absolutely failed miserably at that location. So there's some places where it's going to work super great. Other places it's going to suck. And your goal is to figure out what the pattern is for where it sucks and where it doesn't. Now, how could you do that? Well, what I might suggest is calculating a percent error point by point, and then look for patterns in that percent error. But that's the goal that I have sort of set out for you guys. Are there any questions?
No.
All right. Well, get to it. If you have any questions, you know where to find me. I will happily field those, but that is the thing that I need you guys to do. Okay. One tool that might be of use to you, if you haven't done it before, is conditionally formatting stuff. So for instance, let's say that I want to look at my electric field, and I want to see, at a glance, what all this big sea of numbers represents. So like what I did a minute ago when I was debugging is I went over here and I highlighted cells. So I highlighted all my cells, and then I said, okay, I'm going to go to conditional formatting and make a new rule. And what it's going to do is it's going to color code cells based on whatever rule I apply. So, maybe I like 3 color scales because it gives me more degrees of stuff. So what's going to happen is some of these numbers were somewhere in the neighborhood of a few thousand. So one thing I could do is I could be like, let's make the lowest number on the entire grid be red. Let's let the highest number on the entire grid be green. and let's have the median number be yellow. That's the default. Now, if I click that, what's going to happen is you'll notice, let's zoom out. If I do that, what's going to happen is all the numbers that are far away from the center are red. There's a whole bunch of them that are near the median. And if you zoom in super, super, super close, there's a little tiny speck of green in the middle. Now, why is that? It's because the electric field is super intense when you're super close, and it drops off very, very rapidly. And so the numbers in the very, very center are so much bigger. They're like 1,000 times bigger than all the numbers around them, and that's why I get that little speck of green. But you can also format your rule different ways. If I go back to the conditional formatting and manage my rules, let's edit that rule. Let's change it to something different. You know, sometimes I do it by percentile. If I go percentile, what it's going to do is it's going to take all the numbers in that entire sheet and make the bottom, the lowest 10% of them, make them all red. And here I can make the highest 10% of them all green. And let's keep the median yellow. And you can see that when I apply that rule, you can see that, here in the center, all the big numbers are in the middle. They get wimpier as they go to the outside. That's what I expect to see. You might also try other things. Like, what if I want to be like, let's pick a specific number. And let's have any place where it's less than, let's say, 50,000. Make that be red. Anywhere where it's, I don't know, so 5, 1, 2, 3, 4, 5, 6. There's 5 million. Let's have 5 million be yellow. And let's have anywhere in excess of 5 times 10 to the 10th be green. And you can see that what happens is, man, this drops off super fast, right? It's only bigger than, 5 times 10 to the 10th in a very tiny speck in the middle. And then here, the 5 million mark, it reaches very, very quickly. And by the time I get out here, it's only 50,000 or less. So what you can see is that my electric field starts off super intense and it drops off really, really rapidly. So by changing those rules, you can, at a glance, get a good sense of what you're looking at without having to just blind yourself looking at these ridiculously large numbers all the time. So what kind of conditional formatting rule you might choose to use will often depend on what you're looking at or what you're trying to tease out. So if you're using conditional formatting to make a point, make sure that you choose your rules accordingly and try to extract useful information out of them. I have a history of getting lab reports from this lab where people just unthinkingly, they'll color code a bunch of numbers and they won't tell me what it means, and I don't give them very good grades. So I need you to think this through. All right, that's it. I'm done talking.
All right. Thank you.
You're welcome.
Have a good day.
Okay.